chair and Matthias, already spoke about a lot about sustainability. That made my presentation quite easy. So here, but I just only summarizing only one particular problem currently we are facing. Everyday newspapers, social media, scientific magazines, this particular compound CO2, always we talk about CO2 issues, CO2 related issues, how to tackle that when people talk about capture, sequestration, utilization, storage, etc., etc., etc. So, and you can see that catalyst design, and this is the heart of the technology. If you are smart, I'm a scientist, material scientist, the experience and expertise, how well used to develop the catalyst, and then how that can be scaled up for the technological solution. That's what I'm going to do here. We can say that one, okay, well, I'm not using any automobile, I'm not responsible for the, this global warming. No, we all equally responsible, or at least for some portions, we are responsible. And if you look at this figure, anything that we are using daily that is coming from oil, say for example, whether your shoe or dress or whatever it is, anything that you are using. And it also used for energy source. You can see here. At the same time, we are also depending on these resources already mentioned, that oil, coal or natural gas, whatever it is, or even talking about other energy sources. Over a period of time, the demand is increasing, and you can see that extrapolated one by 2040, this graph is going like this way. It is actually predicted 2015, but you can see that when some of them are exponential growth. And when we do this one, all kind of chemical reactions happen. When you take a coal and you burn it and you get energy, but during that process, you produce carbon dioxide. When you take natural gas, yes, same thing. Or you take even petrol or diesel or whatever, you can see that one producing. Massive amount of CO2 producing. One number provided by Swadhin in this introductory mark, aeroplane. When I put it on the road, if you drive your car 10,000 kilometers, 8,000 pounds of CO2 you are dumping to atmosphere. It's a massive number, and you can see that one amount of, the number of automobiles, coming every household, at least 2, 3, 4 cars are there. Each individual, they are going to drive, and I have 4 vehicles at my home, and I can understand that is a massive problem. No, we don't want to stop anything. This is a part of the development, but when it is a part of the development, what are the solutions we can provide? That's what I'm going to address here. And if you look at this cartoonic presentation, last century or more than a century, and you can see that the temperature is increasing because of CO2 level is increasing, and around 2 degrees. And you can see that one in a website like all this kind of website, or if you go to this observatory in Hawaii, and you can see that every day basis, you can see that second decimal is increasing. And only time actually that came down during the COVID time, because most of the things were shut down, and that as of now today, it's 418.84 ppm. Okay, it was actually gone down to 403 during the COVID time because of most of the industry, car, etc., and all shut down. And it may touch by 450, but that is a mark everybody put forward. You should not cross beyond that one. It end up in series of issues. You can end up in problem with your organs, biological systems, marine life, or agriculture, everything. So you can see a lot of articles. One figure I want to show, this is IPCC report, International Panel on Climate Change. It's published in 2020. You can see that the shaded area, it's going to be underwater by 2050 if we are going in this way. The place we are sitting here probably underwater if you are not going to take a proper attention. It's a serious matter, and we have to take the graph either to stabilize or bring it down to save our sustainable life. You imagine a lot of people living on the seashore, like if you take a city of Mumbai or Kolkata or Chennai and all, and it completely, a massive, problem. And you can also, understand that when many fishermen living with the life, the fishing, and if you want to, catch a good fish, you have to go to the deep sea. And you won't get, the good fish at the seashore. Automatically, the price of, the cost of fish actually going up. You cannot imagine one, seer fish if you want. If you want to buy, it is around 1,000 rupees, 500 rupees. It's expensive compared to last 5 years. So it is a massive problem. But with that, as I mentioned, I am a chemist and I want to showcase certain activities. I will not go to the deep of the chemistry here. However, if you look at the figure here, we work on direct air capture. That's nothing but capturing CO2 from air, concentrated CO2. We also work on, the really concentrated one, but there are technology available. Captured CO2, how to convert into chemicals and fuel by photo, thermo, electro methods. Many chemicals, ethanol, C1, C2, C3. I will show some examples here. We also work in the area of hydrogen production. This hydrogen can be utilized for the reduction of a CO2, or this hydrogen can be used in the fuel cell. If it's fuel cell hydrogen, there is no CO2. On the other hand, if you are using methanol in fuel cell, CO2 will be produced. That CO2 can be captured and then you can have a cycling. So all this process, what is my job is to develop the catalyst to bring down the energy that mentioned in the previous talk and to make it as actually very efficient way of or economical way of processing that. I just bring out the price here. This is published in Nature Catalysis. Sorry, I did not cite here. So you can compare. This is a projected one. Current market price, if you look at here, and produced from CO2. If you take it, scale it up, there is a projection that one, we can be economical process, except methane. Methane is not possible from CO2. Although people talk about CO2 to methane, I also published that one. But it's a difficult task because thermodynamically, there is another counter, and also methane production by natural way, it is a difficult. So all this chemical can be processed, economically if you develop proper catalyst along with the proper engineering. A combination of all together can be done. In JNCASR, what we have achieved, you look at that thermo, electro and photo, all these chemicals we synthesize from CO2. Okay, you can see that around this area, among that one, we scale up methanol to the pilot scale capacity, and then DME and methane. This is up to 300 kilogram of CO2 per day in the JNCASR campus. We tested the facility for the conversion of CO2. I will show the facility. During this period, we designed the catalyst. There are a lot of interesting way to design the catalyst. You can see that you can make it in a different nanostructuring or different types of support metal interactions. That also play a beautiful chemistry at the interface. Or shape, or different types of polymers, adsorbate, core shells, etc. During this period, you can tune this intrinsic activity and increasing number of active sites. So there's a tug of war between what should be optimized. So that optimization needs a lot of research activities, a revisiting of this one. It is with the help of theoretician and our own understanding experimental way of designing the catalyst. So I will take you one first step, CO2 to C1. C1 is actually carbon monoxide, formic acid, formaldehyde, methane and methanol. And if you look at the mechanism, it's very simple for a chemist, probably outsiders maybe it's quite complicated. But you can see that any of this product can be formed, depends on the way you design the catalyst. And I want 100% conversion, 100% selectivity, but practically speaking, it's difficult. What happened actually when it is not 100%, it ends up in actually purification cost. That purification cost depends on what product you are getting. If it is one gas and one liquid, yes, easily can be separated. But if it is two liquid, it is difficult. So that cost will be come into the picture. So how we can smartly do that? We have a lot of work. I will not take too much, but I just give the emphasis. Say for example, palladium and indium, two classical metals. Palladium is well known for hydrogen production. Indium, in the indium oxide CO2 to methanol. We made a bonding between them and then make an intermetallic alloy and cover with the indium oxide, protecting. So the protection is nothing but to protect the oxidation of palladium If palladium oxide is forming, it will form carbon monoxide. So I want formic acid. So to protect that one, I do this one, and then during the course, if it is not protected, you can see that carbon monoxide is getting Faraday efficiency close to 80%. It's nothing great value. Faraday efficiency 100% reported by silver at a different particle size. Or if you want to make a syngas, say for example, syngas is nothing but a standard synthetic what you call fuel for the production of any hydrocarbon you can think about it. So, but the trick is actually how to tune carbon monoxide to hydrogen to have a molecule, a compound that you are looking for. So here this is very fundamental work. We designed this as porous organic polymer with a different metal. Cobalt is favoring for hydrogen production, and zinc we are favoring for carbon monoxide formation. So you can tune, and there is a charge interaction, charge transfer between porous organic polymer and then this metal favoring for the syngas 1:2 ratio, and that 1:2 ratio we can do. Again, this is a photocatalytic green energy way of predicting. Or if you take, Sadhin Mandal already mentioned that one, metal free material, how we can do that one. So metal is always expensive, metal has its own implication, etc. Again, this can be also tuned. You just take a system, it's a planar molecule, and then twist it by design, catalyst design. When you start twisting that, the chemical nature is changing, and it is a selective conversion of CO2 to CO formation. Again, or if you go to methanol, so that is a carbon monoxide and formic acid. If you go to methanol, one work we have done, Professor Bakmar is actually collaborative partner, he did the theoretical calculations in that one. So there is a plant in Iceland that is manufactured, I will show the plant, that is done by, Professor George Oller, Nobel Prize winner, and then Surya Prakash. And the plant is actually, the conversion is 22% of CO2 to methanol conversion. This is a 4,000 ton of methanol per year capacity production. They use geothermal electricity, but they use a pressure 300 bar. 300 bar pressure, you need a lot of energy input in that one. And here, the attempt was to reduce the pressure. You can see that at 20 bar, it's 16%. Compared to that one, that is a 22% of CO2 to methanol conversion. But we have the record now, 30%. I'm not going to show that one. But the idea is actually during the operant condition, that molecule slowly transform into a stable molecule, and that is actually giving the activity. Or if I take another example, again, my aim is actually to keep the feeling that on how the design. If you take a graphene layers are there, and there is a two-dimensional. And like that, if you design a system here, two-dimensional system, when you do this electrochemical condition, this metal can etch it out. And the metal can form oxide. That will change the game. Okay? Here what we have done in this case, this is a two-dimensional, this is a three-dimensional, and gallium is etching out. Gallium is forming a thin layer of gallium oxide. And that thin layer of gallium oxide smartly doing CO2 to methanol process. And we got a record value. This is holding the highest value of Faraday efficiency, CO2 to methanol process. So I am taking a little bit, complicated one. If you go to C2, there are a lot of mechanism reported. If you take an ethylene path, or if you take an ethanol path, all this molecule you can get it. Okay. Along with the C2 molecule, you can get C1 molecule also, carbon monoxide, formic acid, etc. and all. So eventually end up in your product mixture probably 5, 6, 7 different types of compounds there. As I mentioned earlier, purification of this compound is extremely difficult, and that is one of the reasons still the technology is not economically viable. Well, we continue our journey from methanol to ethanol, and we design, I'm just making as a case here, red phosphorus, natural abundant species. And you can see that there is a band gap. This particular, only if you take a red phosphorus, you end up in actually formic acid. And one problem with the photochemistry, there is a easy way of electron hole recombination. So the available electrons are less, and the band edge positions also not in favorable for the product we are looking for. So we tune this material with the band edge position and entrapping the electrons here, and that gives ethanol. And with this one, we also tested this catalyst under the sun over a period of 8 months. morning, evening, cloudy, sunny, etc. and all these conditions we tested. And you can see that in June month, and almost 75% compared to the artificial light that we used. So this is around 35 micromole of ethanol per hour of, per gram of catalyst compared to 55, 52, we are getting. So then we continue that one. Another molecule we designed. This is another example, Bi2S3. Again, what I'm saying that this compound reported. So as a chemist, how to modify the compound in favor of the chemical you are looking for. You can see that's kind of a ladder structure. We introduce chlorine into that one. The structure change. During that structure change, this bismuth 3 plus, that changed to bismuth 2 plus at here, and bismuth 3 plus, delta plus and 3 plus, delta minus, charge polarization. When this charge polarization come into the picture, the intermediate coming, that is nothing but CO and CHO, stabilizing, and it is forming CC coupling. So to stabilize that CO and CHO, design this catalyst, and then eventually you end up in ethanol here. Ethylene, again porous organic polymer, and we tuned this one charge transfer from polymer to the metal, and that facilitating proper carrying, and either this kind of organic moiety or this kind of organic moiety that will tune the charge transfer and then charge what you call band edge position. And with this one ethylene we got 98.9% selectivity, 98.9%. Again, I don't say that it can be scaled up. It is not possible because it's a photochemistry, efficiency is less, it is very nascent stage, and we cannot do it at the moment. And then we continue this one. You all know that one zinc sulfide. Most of might have studied in +2 class or at least in the BSc class. Zinc sulfide, Wurtzite structure. And you take a copper on the right side, left side, and gallium on the right side, copper plus and gallium 3 plus. Substituting at copper, and you get, zinc, and you get a charge polarization. Again, that is also giving ethylene. And here we improve the record. It is a 200 micromole per gram. We are holding the highest record of ethylene in terms of yield by photochemistry here. Then acetic acid, I'm going through fast, and then we got a very good Faraday efficiency close to 0 potential, very close. And we continue to propanol, and you can see that particle shape we control, either it is a sphere or cube. When it is a sphere, the crystallographic surface will be different. Packing density of atoms are different, and that will actually, both are giving propanol. If the packing is better, that will give more propanol. And we got a propanol close to 17%, and this is considered as one of the best, in the current scenario in propanol. And then we continued butanol, and here we take a simple Fe3O4, iron oxide. This is also natural dependent. If you take just iron oxide and heat it at a high temperature and pressure in the presence of carbon dioxide, it will form iron carbide. That iron carbide, there was a talk, olefins, it will easily form olefins, like butylene, propylene, etc. and all. So what we have done actually introduce indium into the lattice, and that even change, create a strain within the system. The strain actually push the Fe3O4 into different oxidation, different coordination environment. So that change the mechanism end up in higher alcohol, like a butanol, pentanol, heptanol, and even isobutylene. Whatever the cosmetics we use, the fragrance, isobutylene, that also we got from this product. So, but that is a very small amount, it's only 2%, 3% only, but higher alcohol we got a large amount. So what we have done, the amount of CO2 absorbed at the surface, and you can see that it is increasing with another modification, it's increasing. So I have taken all this, we have published almost maybe 25 papers, including original article, review article, viewpoint article. What is the idea actually? How the journey from, the basic one, how we can improve the catalyst, chemistry to have a better product distribution. This is the first warning, right? Okay. So product distributions, we can do that one. So the dream project, probably photosynthesis, you never know. That can, how you can mimic that photosynthesis in the laboratory and get as good as or better as CO2 to glucose if we can produce. Anyway, I will take one product out of this, all this one product, methanol. Already mentioned methanol economy. You can see that lot of advantage. It can be used in fuel cell, more stable than hydrogen, sustainable, renewable, multiple application, eco-friendly, etc. and all this were there. And if you look at the energy content per volume, you can see that starting from diesel up to hydrogen and higher ambient condition or higher vertical pressure, etc. You can see that methanol is somewhere in the middle of that one. It can be considered as a good, fuel. And also government of India proposed methanol economy. It can be blended M15, or even Chinese company, they already introduced the cars actually M100, 100% methanol based engine. Or if you go to Israel, they have, Italy, they have A20, that is ethanol, methanol, and together with the diesel, that can be. So this is considered as a fuel. This is not a new one. 1973, there is a science article, written by these two gentlemen, and then you can see that they proposed methanol economy. At that time, the boom of ethanol, E10 came into the picture slowly after some time, and even it was introduced in Chicago. It was introduced in Chicago, and you can use it, even the cold condition also. Somehow it not turned out to be good, and Professor George Ola, and he was a student of George Ola, and they started the work way back in 70s and 80s, and he got Nobel Prize in 91 for his contribution to the carbonate chemistry. And they started a company in Iceland. The reason I can tell you, Iceland they started because of the geothermal electricity. The cost of electricity here in India approximately 7 to 8 rupees if you are using the grid technology. But this is very cheap, and you can see that around 4,000 ton of methanol they produce at a higher pressure and everything. And there's another project here in Germany and a couple of projects in China, etc. and all. It took almost, 8 years, 9 years to reach the TRL level, technology readiness level by 8 or something like that one. Okay. But this plant cannot be taken into India because electricity cost is high. Hydrogen is actually cost is also very high. It's very difficult. So what we have done, we started this journey in 2015-16, and I just introduced one term, space-time yield. That's nothing but gram of methanol in a gram of catalyst in an hour. So typically, publication comes conversion and selectivity, but if you want to go to the next level, it is not the one. We have to consider all together. So you can see the generation of the catalyst, my students, develop, and also in collaboration with the Pune, NCL Pune. And you can see that during the period, there are papers came into Science or Nature, etc. It's a healthy competition, but we hold, record of 5 catalysts at the current scenario with the best space-time yield. I'm not saying that one, we scaled up. We only scaled up this well. So most of the catalysts we cannot scale up because of various reasons. So what we have done, we started a company way back in 2016. I'm not going to the detail. And we also came into the picture of, Stellaris noted companies in the various area, and then you can see that in carbon sequestration along with the carbon clean solutions, we are already listed in that one. And carbon clean solution, they recently commissioned a plant of a 5-ton capacity of CO2 capture from steel, and Tata Steel, they started that one. Anyway, this is the technology, this is the CO2 capture, we have a partner, and this is the technology we have developed. I'm not going to any engineering part, but there are engineering partners involved in that one. And then recycling and the product distillation, and finally electrolyzer, and we all integrated together, and we demonstrated this technology at a various platform, both national and international. And we also got the ISO certificate in that one, that is available in the website. You can download and then understand the technology. And the technology life cycle analysis of the technology done by University of Calgary, and then endorse the technology. This can be a carbon neutral technology with a condition if the hydrogen is producing from renewable energy. Okay, so this is a plan, this is a building in JNCASR, and you can see that various stages starting from catalyst synthesis, reactor, and various control unit, and then you can see methanol distillation. Finally, you can see that methanol collecting by the student. So this is 300 kilogram of CO2 per day capacity that we have done at JNCASR. I just bring the cost of the item. 1 minute I will finish. Yes, so here we calculate the cost, it's in the range of 20 to 24 based on the utilities. Okay, it can vary if the CO2 amount, if it's a what you call food grade CO2, the cost will come down. And if you compare the market value, this one, and you can see that the market, I mean, particularly China or Asia Pacific region, how this is actually. Currently, we are working with the CMPD and CAL, Coal India Limited, to build a plant with a capacity 1 ton in the single cycle 500 kilogram. And you can see that this is a 650 megawatt plant, and this is a chimney, CO2 coming from here, we capture and purify. And around 3 kilometers, we are building the facility for the conversion of CO2 to methanol. And we have also anyway Center of Excellence funded by DST, the generous fund for 5 years. This is actually to make a strong network within the country for the sustainable solution, particularly in the area of carbon capture and utilization. And I welcome all of you. I mean, so we can interact if in any common practices there. So finally, I would like to thank my team. There are good bunch of, so very strong, group of students. They develop this catalyst and scale up the catalyst. I can tell you, I scale up the catalyst, I mean, even with a capacity of 10 kilogram per batch capacity at the site. We, I mean, customize that one. But beyond that, we did not work. We have to work with the big agency. So my last slide. So we are making the tree of products from CO2. Okay, we are growing, but at the same time, we are going to the root also from CO2 to carbon nanotube. We made this one, but we yet to understand the chemistry there. It is in the early stage of the result because it's a lot of challenges involved. With that, thank you very much.